Welcome. I'm sure that none of you have been able to escape the numerous environmental strategies that surround us these days. And on the back of those, what we're seeing are a number of procurement processes which include carbon accounting. And what I want to take you through today is a quick peek at pipeline systems specifically and how we can address the issue of carbon accounting within pipeline systems. I'm going to focus here on gravity drainage and sewage, so wastewater systems. However, many of the principles that we're going to discuss and look at will include other pipeline systems and other areas within the industry as well. So it'll be a whistle-stop tour through the carbon accounting process, specifically looking at pipeline systems. So first of all, let's just clarify what a carbon footprint is. I think there's probably some confusion, or potentially there's some confusion as to what we quote when we say what a carbon footprint is. And I think the first really important point of clarification is it's not just about carbon dioxide. There's a big myth out there that carbon accounting is all about CO2. The answer is, yeah, CO2 is a great big component of our carbon accounting, but not necessarily the beginning and the end of the story. We need to also address and understand other greenhouse gases, those that will create what we know as radiative forcing, the ability to entrap heat within our atmosphere. And therefore, we look overall at other emissions, other substances that can lead to entrapment of heat within our atmosphere. And therefore, we look at products and the activities associated across the supply chain contributing to climate change. So climate change is the big focus. We then convert that into what's known as carbon accounting or carbon footprint, but it's more than CO2. There's also a process known as life cycle analysis, and that certainly is a bigger picture than the carbon footprint alone. Carbon accounting only looks at the climate change component of a life cycle analysis. So if we're looking at the carbon footprint, that's not the whole story. Even if we take it across the entire life cycle and stages, from cradle right through to grave, of the whole process. So let's clear things up. Carbon dioxide is not the only part of carbon accounting. Carbon accounting is a small part or a component of life cycle analysis. What we need to do is look at other gaseous emissions in addition to carbon dioxide. And what we do is we look at something called a global warming potential, which is this radiative forcing effect. And what we do is we look at other gases and we contrast those to carbon dioxide as an equivalent value. So for example, as you see here, we have other non-CO2 elements such as methane, nitrous oxide and so on, which are given by their weight an equivalent to carbon dioxide. So in this particular example, what you see is the current carbon equivalent for methane is 25. In other words, it's 25 times more efficient at entrapping heat within our atmosphere. So 1 kilo of CO2 equals 1 kilo. 1 kilo of methane equals 25 kilos of carbon equivalent. And so the measure that we use is not CO2, but CO2e, the CO2 equivalent when we look at the other greenhouse gases. Now there are useful methodologies, there's ways of assessing the things that we're measuring and looking to manage. And BSEN ISO 14040 is a starting point, and its brother publication 14044. And in the UK, there's a very useful publication, very recently produced by DEFRA, which is the publicly available specification, PAS 2050 for short. And that very much gives us a good, reliable set of methodologies and recognised guidelines for carbon accounting. Now, many companies refer to online and published carbon databases. And one of the key issues we have with carbon databases is that many of these databases are CO2 only. They do not account for other greenhouse gases. So beware, if you're looking at a carbon database, understand whether it's CO2 only or whether it also incorporates other greenhouse gases. It's important that when we look across the supply chain that we understand whether we're taking a snapshot or whether we're looking at the big picture. And it can be dangerous to assume that if we're looking at a subsection and taking that as being the lowest impact, we may have a very different picture when we take the whole scenario into account. one recognised example of a credible, recognised carbon database is the Bath University ICE database. It forms the basis of many carbon accounting models. And indeed, the Bath University database is principally carbon dioxide only. It does not incorporate other greenhouse gases. Now, it's really important to understand this because some materials are very much carbon dioxide only. Other greenhouse gases have almost no effect on their total carbon footprint. But other materials can have a significant increase in their carbon footprint if you incorporate the other greenhouse gases. Plastic materials are one such example. And as you see here, we're looking at HDPE and PVC, two very common pipeline materials. And as you see, with the Bath database, we have 2,000 kilos for HDPE and 2,500 kilos for PVC. That's because we're only looking at the carbon dioxide value. But if we incorporate the other greenhouse gases, we get a very different picture. There's a European-produced plastics industry report that relates to their own products. And if we look at HDPE and PVC within the Plastics Europe study, which includes the likes of methane, which has a substantial effect, what we see is that 2,000 kilos for HDPE escalates to 2,500 kilos, and likewise with PVC, we get 3,200. So we're looking at 25%, 30% increase in the carbon footprint of a material when we incorporate the total greenhouse gas emissions associated with its manufacture. So, first point of interest. Recognise and remember that 2,500 for HDPE because we'll be revisiting that later on in the presentation. Okay, for my own convenience, I've used the term boundary condition. People prefer to use system boundaries, product system boundaries. But what I'm trying to show you here is that if we look at the entire picture, the whole supply chain for a pipeline, it clearly starts from the manufacture of the product and ends in the decommissioning and the removal of the product end of life. Now, if we are limited in the view that we take, if we take maybe just the production of the product or the production of the installation, which is sometimes the only interest of a particular business, you're not necessarily looking at the whole picture, and therefore if you're making a purchasing decision based on the carbon footprint you're allocating to only a part picture, you may not necessarily be getting the lowest overall impact. So do understand when you're taking a snapshot versus a holistic picture. I think the other point to appreciate is that it can be much more difficult to find good, reliable data for some of these boundary conditions. So another reason why sometimes people are shunning away from some of the analysis is that we just simply don't have the data. It's far too difficult to actually get the models in place. So, first of all, let's look at the Cradles Gate, which is essentially the manufacturing process. And of course, what we look at are the raw materials and all the elements that go into the manufacture of the product, or in this case, the pipe. And of course, we also can look at the contributing effect of any recycled materials and use of co-products and waste streams. But we also obviously need to look at the manufacturing process itself and all the impacts associated with making the product as well as the materials used to produce together. So, first example, let's look at concrete pipes. Now, concrete pipes is an area where I can report with a high degree of reliability because I represent the trade association that manufactures concrete pipes. So we've looked at our own data very carefully, and I can assure you that with a lot of stringent analysis, this data is as close as we know to being reliable and correct. And what we see here are the components that come together to make concrete, including concrete pipes. And so first of all, if we look at the aggregate components, what we know is that when we win the aggregates from the ground and we put those aggregates onto a truck and it's ready to go to its supplier, then we've got 6, 7, 8 kilos of CO2 equivalent associated with that activity. Now, with some of our manufacturers, what we find is that we do partially replace some of the aggregates. For example, some of the finer aggregates in the form of sand is replaced by ground glass, recycled glass. So there are offsets that we can accommodate within recycled raw materials on the aggregate side. Secondly, we look at the binder that's putting all the material together, and that's typically Portland cement. But virtually every single concrete that's made these days incorporates another material, typically fly ash or granulated blast furnace slag, which offers certain properties to the concrete, but also will reduce its carbon footprint because they're byproducts or co-products of other processes. And within the manufacture of precast concrete pipes, we're typically using about 30% fly ash, offsetting the amount of cement that we're using. And therefore, what we have is between 640 and 680 kilos of carbon dioxide equivalent of the cement component. Moving on, if we look at the water that we're using, if it's coming out of a borehole, we're getting that for free. But if it's being processed by a water company and supplied via mains, then we have a 0.276 carbon dioxide equivalent for that part of the process as well. And then we have other few bits and pieces, minor constituents that go into concrete, for example, the admixtures, which are a very small proportion to the total, and reinforcement. Some pipes are reinforced, not all, but when we use reinforcement, it comes from a recycled stock of steel, and therefore we have a proportionally lower than virgin steel component that goes into the manufacture of reinforced concrete pipes. The other point of note is that virtually all the raw materials that go into making concrete pipes is locally sourced, and 99.8% I would treat as being virtually all. So what you see here is less than 20 kilometres on average for the aggregates coming to the pipe production plant, less than 100 kilometres for the cement, and just under 200 kilometres for the reinforcement steel when it's used. So that, when we bring all that together, what that tells us is that the transport component bringing all the raw materials together for the manufacture of concrete pipes represents about 2.5 to 3.5 kilos of CO2 equivalent per tonne of concrete pipe. What I'd like to also just introduce you to here is the concept of pipe miles. I'm sure that many of you may be familiar with the concept of grocery miles or food miles and what's been reported through the supermarkets of recent times. I think that the same could be said for the manufacture of pipes and where they're originating from in terms of their source materials and where they're going to. If we look at the manufacturing process of concrete pipes, then there's a number of activities that come together to make the pipes. And when we look at all those processes and analyse those together again, what we find is that there's just over 21 kilos of carbon associated with the manufacturing process itself. So bundle all that together, and what that tells us is that when we're looking at concrete pipes, we have between 138 and 150 kilos of CO2 equivalent per tonne of concrete material. And the higher and lower values will depend on whether particularly we've got steel in the pipe or not, whether it's unreinforced or reinforced. And to give you an idea of what that means in terms of pipes, just a quick snapshot for a couple of pipe sizes. If we're looking at a 300mm diameter pipe, then that would suggest that we're looking at 23 kilos of CO2 equivalent per metre length of pipe, and a 600 diameter pipe, 73. The second example is looking at another commonly available pipe material, and that's plastic. But plastic materials perhaps are rather more complex to analyse than concrete because there's a whole raft of different plastics materials. We typically have high-density polyethylene, polypropylene and PVC pipes. So already we have a bit of a more complicated analysis to do in looking at those different materials rather than concrete, which is much easier to average out as a common material. But what we know about plastic is it's an oil or gas, natural gas derivative. It's hydrocarbon based. And what do we know about hydrocarbons? Well, they're distributed all over the world, and therefore to bring our raw material to the UK, we have to consider maybe considerable haulage back into my currency, pipe miles. So the resin, what we're doing is we're refining the oil, we're converting that refined material into a resin which becomes the basis of the manufacture of the pipe. That resin would be an HDPE, a PP or a PVC resin. So where's it coming from? Well, we reckon that there's about 10 to 15% of the resin that's actually UK based. Other common areas to source the resin would be Europe. The majority would be sourced from Europe, places like Netherlands, France, Poland and Italy. But there's also a very strong chance that resin can be sourced from the Middle East, Far East and the Americas. But if we look again at the Plastics Europe study, then what it tells us is that the Cradle to Gate and life cycle reports that are commonly available would take a 100 kilometre one-way delivery for that raw material, for the resin. And if we look at that as being our basis for analysis, it tells us that we have just over 8 kilos of carbon equivalent per tonne of a plastic pipe based on the 2009 DEFRA conversion factors. But if that resin comes from other sources, for example if it's coming from Italy, then the transport component would be about 70 kilos more. If it's coming from Saudi, then it's about 170 kilos more. And moving right across to India, then of course we have even more pipe miles. So it's important to understand that we have a much more complex picture when it comes to analysing plastics pipes in terms of the different plastics materials, but also where the pipes are being made and where the resin source is coming from. Okay, other things, just to make life even more interesting, we have what's known as electricity conversion factors, which are annually updated, whereas other figures can be updated on a more long-time basis. And what we know is that the UK, for example, currently is on an increase. In the long term, it will be on a decrease once we introduce renewable energy forms in proliferation. But places like Germany and Italy already have substantial renewable energy sources, and you can see here that they have something like 25–30% lower energy conversion factors compared to the UK. And that will make a difference depending on where the resin is coming from and the energy conversion factors of that particular source of country. To give you an idea, if we're looking at concrete coming from Germany, you would expect to be reported as a lower figure than in the UK. Now you may remember that I mentioned a few moments ago that our analysis tells us that in the UK, concrete pipes has a carbon footprint, cradle to gate, of 138 to 150 kilos per tonne of material. It's going to be more like 100 to 130, 140 in Germany. Lower, principally because of the different electricity conversion factors. Another example, if we look at plastic pipes, remember that 2,500 that we talked about a few slides earlier for HDPE? Well, the Plastics Europe study relates to a European value. If we look at a UK manufacturing and resin source, then what that tells us is that 2,500 will actually move up to over 2,900 kilos per tonne of HDPE material. So again, it's complex and it can be potentially misleading if you get your numbers and your sources from the wrong places. And just to try and unravel this a little bit, I don't know whether this unravels or adds to the complexity, but if we take, for example, a 450 normal diameter pipe, then our calculations tell us that a concrete pipe would have a carbon footprint, cradle to gate, of 37.4, get that one, 37.4 kilos of carbon dioxide per linear metre. Depending on where the resin is coming from, and looking at the different source data for the energy conversion factors of those countries, it tells us that if our resin, our HDPE resin for a HDPE pipe is locally sourced, then we have a cradle to gate carbon footprint of 46.8 kilos. Interestingly, it comes down if the resin comes from Italy. So the decrease in the energy and the energy conversion factors more than offsets the increase in the haulage and the transport component. But if we then look at sourcing from Saudi Arabia or from India, then clearly we go pushing way up in the other direction again. So the resin source does have an important relationship to the transport miles, but also to the energy conversion factors that we use for that member state. Now, looking at gate to site, so we're moving on now to the next boundary condition, as I call it, and that's the gate to site implications. In terms of transport, it's well recognised that there's far less material in a flexible plastic pipe, whether it's HDPE, polypropylene, or PVC. And therefore, there will be transport savings, CO2 savings, in relation to the lighter weight flexible pipes made from plastic compared to concrete and clay. But it's also important to understand the installation process and how we put the pipes in the ground, the structural design and the engineering principles that we adopt for actually installing these systems. And when we look at flexible pipes, what we know is we have to use, as a minimum, a full granular surround. So we have essentially one option, and that option is the full granular surround. That has implications, particularly when we can look at rigid pipeline systems, typically concrete and clay, where we can engineer alternatives to the full granular surround. And when we're able to do that, and our structural analysis allows us to move away from the full granular surround, we can take advantage of the lower carbon footprint from the virgin granular material that we need to use for the bedding of the pipe, and the associated transport to site of that granular material, and the associated disposal of the excavated material from the trench. There are some areas of common ground, and one, for example, would be the use of mechanical equipment for the lifting and the positioning of pipes. All pipes over 300 millimetres diameter, whether they're flexible or rigid systems, should, if health and safety best practice is being used, should all use mechanical lifting equipment. So the implications in terms of energy on site should be on an equal basis. So let's have a look at an example in relation to the gate-to-site component. So this is not including the manufacturing process, the embodied content of the product. This is purely the gate-to-site process. And in this example, we have 2.1 metre HDPE pipe, where the total sums up to 143 kilos of carbon dioxide equivalent per metre length. And that comprises of a full granular surround, and we require almost 5 cubic metres of granular per metre length, so that's 86 kilos. We then transport it, and in this instance we're saying 30 kilometres from the source of the aggregate to the site, and there we have our carbon footprint for the transport, and that's the associated delivery of the pipe itself, so 11 kilos per metre based on a 100 kilometre travel journey for those pipes. And then we have to remove the excavated material from the site and dispose of it, and another 30 kilometres, let's say, to the landfill site would give us another 23 kilos. So add that all up, 143. Again, if we compare that to a concrete pipe, and we are able to move away from the full granular surround, then it does make a difference. And what we see is that without the use of a full granular surround, the amount of granular material is reduced, so there's a corresponding reduction in the carbon footprint of the aggregates required, the granular material. Again, a 30-kilometre journey would give us the pro rata amount of transport emissions, and likewise the equivalent reductions in the disposal. Indeed, what we do see here is that there's an increase in the transport emissions, assuming, of course, that we do have a consistency on the transport distance and the haulage. If we happen to have a difference between the manufacturing site and the construction site, then of course we need to take that into account as well. But on this basis of a like-for-like haulage distance, then we do see that this shows us a reduction for the lighter weight HDPE pipes, but overall there is a difference here. When we get to the area of operation and maintenance, this is one of the areas which is much more difficult to quantify. In terms of getting good, reliable data from water companies and licensed operators, this is perhaps the area that needs more work. This is work in progress, more development is required. So we're going a little bit anecdotal here, just to try and get a flavour of the sort of things we might consider that might be appropriate within the analysis and the detailed number crunching when we get to the data here. Concrete pipes, what we know is that concrete pipes have been in existence for well over 150 years, many of which are still going strong. So we have a good long track record of empirical evidence to rely on. And indeed, there are many recognised design guides and published documents which will state that concrete can have a design life well over that 100 years in any event. And perhaps uniquely, what we know about concrete is it does get stronger as it gets older. And interestingly, modern concretes, with the incorporation of PFA and GWS, these select additions, that confer certain properties on concrete will also reduce the alkali silica reaction. They will actually retard the strength development of concrete to a certain extent. So although the concrete needs to meet a certain strength requirement at a particular age, it will go on increasing even more strength later in life. So actually modern concretes will potentially be even more durable than concretes that have already proven themselves to last 100, 150 years. Plastic pipes, well, unfortunately we just do not have empirical evidence of any plastic pipe over about 50 years. So we're venturing into the unknown beyond 50 years. Not to say that they won't last as long as perhaps they claim to last, but we just don't have the evidence. But certainly there are many newer materials, newer plastic types and structural designs of pipe that certainly don't have even a 50-year track record. And so again, we're venturing more into the unknown in terms of how long these materials will last. But what we do know is that converse to concrete, which will gain strength over time, plastics can deteriorate and deteriorate quite quickly in terms of their mechanical properties. And if we look at the E value, Young's modulus, then what we know is that there is a potential for plastic materials to become embrittled very rapidly. So throughout their life cycle, we know that flexible systems are designed to deform, that's their structural mechanism. We know that the whole range of different types of plastics materials means that there's a whole degree of wide range of rigidity or flexibility to those pipes, but certainly those that are more flexible may be venturing closer and closer to a defect condition because of the age-related deterioration in their properties. But also, it's not just the structural components, there's also hydraulic implications of flexible pipes when they deform. So we're moving away from the carbon footprinting area here and looking at the functional performance. End of life. Okay, move to the next boundary condition, end of life. Many examples exist of concrete pipes that have been dug up over 50 years old and have been found to be in such good condition. Guess what? They've been tidied up and reused for another contract somewhere else. So they are actually reusable as well as being recyclable. We can recycle structural concrete, including precast concrete pipes, end of life, break it up as rubble, and use it as an aggregate or as a fill material. Downcycling is a very term that's used. But also, interestingly, and perhaps sinfully overlooked many times, and that is that concrete, just like trees, actually sucks in CO2 over its life. And none more so than when it's ground up as a rubble and a large surface area is exposed to atmospheric carbon dioxide. And that allows a process known as carbonation or recarbonation to take place very rapidly. So, if we are grinding up the concrete material end of life, it's been determined by many research projects worldwide that we can have between 15 and 35 kilos of CO2 equivalent absorbed back into the concrete per cubic metre. And if we take the total life cycle of that concrete and the carbonation that would take place over its life cycle, there's probably another 10 in that. So overall we have between about 25 and 45 kilos of CO2 absorbed end of life of concrete. Now, if you remember the DN450 concrete pipe that we looked at earlier, we had a number of 37.4. So what that means is that we can reabsorb about 10% of the CO2 associated with the Cradles Gate emissions of a concrete pipe through the process of recarbonation. So there's a carbon negative effect to take into account. If we ignore that in our accounting process, then we're missing one of the very important factors that leads to a more sustainable pipeline. Plastic pipes, well, I'm not sure that they're reusable at the end of their design life. If they are able to be recycled, they certainly wouldn't be recycled in the material used in pipes. You need to quantify the characteristics of the material, and one again would suggest that it would be downcycled if it's recycled, but not used in a new pipe. Quality control is paramount within that manufacturing process. So, just to review then, if we're looking at carbon accounting, what we must do is relate it to an accepted methodology. And perhaps the most appropriate one for us to look at these days is AS 2050, the publicly available specification, free to download from the web. We need to understand the boundary conditions in the context. If you're stating a carbon footprint, ensure that we understand what boundary conditions you're considering within that analysis. show your source data, your calculations and your assumptions as 2050 tells you that's what's required. But what we must understand is that if we're going to fully quantify all the life cycle stages, there's still more work to do. We haven't fully cracked that one yet. Getting reliable data across the life cycle is essential. Now, what we have been able to do is have a first pass at looking at different sized pipes and analysing some of the carbon footprints, the CO2 equivalents, based on cradle to gate, gate to site, the installation, and a bit of recarbonation in the case of concrete pipes. And what you see here is the case is not clear. There's perhaps what you might call an overall winner, but you have to be very careful in looking at the specifics of a pipe, the brand, the material, and the nature of the installation to understand what gives you the best result. And as I say, this does not incorporate the boundary condition 3 of the operation and maintenance implications. It only partially tells you a story of the end of life implications as well. So here's a snapshot, be wary of snapshots. And so, I think what we understand is that carbon accounting is complex. It's not just about CO2. Reliable data is absolutely key.